start now. Alright, hey guys, welcome. Today we're going to be going through Windows Ransomware Detection. I'm really excited to present this to you guys. So yeah, without further ado, let's dive in. So to understand how to detect ransomware, we first need to get an understanding of how ransomware on Windows work and the generic overview of the operations that it takes before the encryption and during the encryption. And if we do this to gain a better understanding of how we can actually detect these operations. So first, let's start what happens before actually ransomware starts encrypting stuff. If you guys were around for the Conti ransomware sample, a lot of this should look familiar. But for those who aren't, yeah, let's kick into what happens before the encryption. So before the encryption, ransomware typically likes to prevent and inhibit system recovery. It does this by deleting these volume shadow service copies. These copies are used to make backups of the drive and allow companies to restore the encrypted file system. Operators typically do this to kind of increase their chances of being paid by these companies. If they don't have any sorts of means of backups, then the company's forced to pay the ransom as they're unable to continue business without it. And they typically attempt to do this via using the command line utility, such as like the VSS admin util or a WMIC, or there are many different ways to do this. We'll dive into them in the next couple of slides. And also before they encrypt files, they attempt to stop and disable endpoint security products. This is because these security products that lack anti-tampering kind of have these detection rules and prevention rules to prevent these utilities such as VSS admin or WMIC from being used maliciously. And this allows them to, yeah, well, just delete the VSS shadow copies. Also, these endpoint products may use like Canary files or other sorts of detection means to catch the ransomware during the encryption. And by disabling these products, they inhibit them from actually detecting and preventing the ransomware. And they either do this by attempting to terminate or stop the service of the endpoint security product, or they'll do this by rebooting into safe mode. Safe mode has been used by some ransomware groups in the past. It requires a reboot and a registry write. Another reason for stopping or terminating processes and services is that these files, such as like database applications, hold an exclusive lock to these database files on disk. So by terminating and stopping these services, they free up the file lock to that file, and they're able to encrypt it. Alternatively, as you've seen with Conti, they use something like Windows Restart Manager to obtain an exclusive handle to the file. And also before the file encryption, they'll do file system enumeration. So typically this just looks like from A to Z drive, they'll do a depth first search or using find first file of all the files. They'll push these files into a queue, and then they'll have separate worker threads to encrypt these files. The next step is to drop the ransom note, and during the they'll either do this in the root directory, so C drive, or they'll do it in every directory that they enumerate. There are some detection opportunities here. We'll get into them later. And then during the actual file system encryption, the first thing they do is, yeah, they obtain the handle to the file with read and write. If they're unable to do this, they'll attempt to terminate the process that owns an exclusive file lock, either through Windows Restart Manager or using the native API. And then, of course, the actual file encryption. So different ransomwares have like different options on how they encrypt the file. So some do partial encryption, some do full encryption, and some have variable amounts of encryption where based on the file size, so whether it's 1 MB or 10 GB, they'll encrypt different amounts of the file. So for example, a PDF that may be like 10 MB, they'll encrypt the entire thing, versus a database on disk, they'd encrypt 10% of it, like every other page, for example. So yeah, let's dive in a bit more what happens before the encryption into those individual stages, and let's look at some of those detection opportunities. So to kind of understand why they're interested in VSS and why they manipulate it, we need to understand a bit more about the actual service. So volume shadow copy service is a service that's provided by Microsoft and allows people to create point in time copies of the data. These are shadow copies. So for example, as you guys see, we have device hard disk volume 1, and then we may have another object in the global namespace for the shadow volume copy. This, where it's n, doesn't map directly to 1. It's just a unique number that maps to that hard disk volume. And Microsoft provide two mechanisms to have these for these providers. The first mechanism is a complete copy, and this uses the same amount of storage as the volume, so it's like 1 to 1. And then the alternate option is to have copy on write, so any writes to the original volume 1 are also made to the shadow copy, and that allows for to see the differences. So what you'll typically see be done is that you'll take the complete copy. These two mechanisms can be used together, for example, so you can use the complete copy and then you can have the copy on write, and this allows to restore the entire disk by first taking the complete copy, then applying all the copy on write changes to the copy to restore it. And Microsoft provides their own default system provider for shadow copies, and that's enabled by the Volsnap system driver and the DLL that you see in user mode. And this provider leverages copy on write. Most people, like 99% of the cases, you'll see is that this provider is used. And in terms of actually deleting these volume shadow storage copies, in Babok, for example, they just use the VSS admin utility and they specify delete shadows all. And this is just a command, so it's quite easy to detect and prevent. Whereas in the example of Conti, they use the WMI to query all the IDs of the shadow copies, shadow copy volumes, and then they specify using the command line to delete where the shadow copy ID is equal to the one that they retrieved earlier on. Another utility that you can use that Microsoft provides is the disk shadow utility. They're not any public samples of ransomware that use this utility to delete the volume shadow copies, but it's there. So in terms of actual detections for these command lines, we'll break it down. So for these actual VSS malicious operations, we'll break it down. We'll start with the command lines, and then we'll dive into how these command lines can be almost evaded and kind of the limitations of existing detections. So to get telemetry for these command lines, you obviously need a kernel. Well, you can either do it two ways. You can do it with the kernel driver, and you can register a callback to receive notifications on process creation and exiting. We're only interested, of course, in process creation to see the command line that was created. So this will typically be done with the ps set create process notify routine, and this when you register a callback, within the callback there's information about the command line, and to almost veto or prevent a process from being created, we set the creation status to an NT status error code. And we do this, for example, if it matches like a regex rule for um, let's say vss admin.exe delete or shadows, for example. The other option is with event tracing for Windows, and the only problem with this is that it's asynchronous and it's not real time, so there's really no opportunity to veto or prevent these VSS command lines from being abused. So let's go into an example from like Elastic, what these kind of rules look like. So we can see they have a rule where the file name is WMIC and the command line has shadow copy and delete. We can see this maps back to this example from Conti, and this would detect that Conti example. Or another scenario is to use the VSS admin, and they have it where it's got like shadows, or it's got delete and resize. The reason why they have resize, so when you've got a volume shadow copy, these shadow copies can be allocated a max storage space, and if you resize it to a small enough space, that shadow copy essentially disappears as it doesn't have enough storage to store the shadow copy. And that's another way you'll see ransomware groups detecting it. I mean, ransomware groups using VSS admin is to resize the storage into a space small enough where it's essentially deleted inadvertently. Interestingly enough, Elastic lacks detections for disk shadow delete, and we can see the problem is that, like, to create detections for malicious VSS usage, just having it at the command line detections, while it's great, it doesn't address the underlying mechanisms these utilities use to actually perform this. And this inherently is just CTL codes. So we'll see later that you can just replicate this functionality and get around these detections. If you're interested in these actual rules, you can check out their repository at Protection Artifacts and just search for example, VSS admin or shadow copies. So the first way to avoid these command line detections, because, well, EDR have got really good at detecting malicious command lines, because they've got the telemetry that they can. It's really just simple, like regex rules, and it's they've got great at doing it. So the first way to avoid this is just run the executable in memory. So you can just do this using for example, there's an open source tool by Fortran called No Constellation that allows users to run executables in memory without creating the signature of the process creation signature and callback. And yeah, there are many readily available open source implementations. I haven't seen any ransomware groups use this kind of thing to avoid these detections, but it's quite simple to just like specify the process you want to create, specify the arguments, and this kind of gets around these command line detections because there's no kernel callback created when these processes are created. I wouldn't say the process is created, it's just the functionality is re-implemented locally within our local process context. To Another better alternative is to use the COM providers provided from Microsoft. So Microsoft provides two COM providers for this specific purpose. So there's one to delete the snapshots, as we've seen earlier, and then the other one to change the maximum area of like the volume shadow storage space is to use the second provider we can see here. As I explained earlier, we can set it to the smallest acceptable size, which is 1 byte in this case, and in turn, this causes the shadow copies to disappear as there's no storage space available for them. Taking it up a notch, we can actually reuse these IOCTLs from these that inherit these providers and CLI utilities use underneath. This approach was first documented by Fortinet in 2020, but of course, if you just search for the Windows source code, you can find these IOCTLs and you can re-implement these functionality by, well, just looking at what the Windows leak source code does. And at the heart of all these, the providers, the command lines, they all use the same IOCTLs, and to actually detect and prevent it, it requires the IRP filtering at the kernel level. This is because this is as VSS doesn't inherently have any access control at the kernel level. All you really kind of need to do is open a handle to the volume, so like hard disk volume 1, and send that IOCTL code, and that kind of gets around both the command line detections and any endpoint security products that don't perform IRP filtering at the kernel level. So, for example, if we wanted to delete shadows, we could use the IOCTL volsnap delete snapshot, and we'd first open a handle to this volume shadow copy, and we'd send this. IOCTL to it. Or the other option that a public proof of concept is available for is to use the set max diff area size, and we can have a look at this here. We can see that it just opens a handle to the volume, and then it just sends the IOCTL to the volume, and this requires, of course, admin, but it deletes all the shadow volumes for this volume. And if you have like a quick Google for this actual IOCTL code, you see a growing number of ransomware groups are starting to leverage this as well. It's a lot easier than, well, it's a lot more evasive than just running the command line, and it's really just, as you saw, it's quite easy. It's just one IOCTL code. A lot of these groups are just leveraging this proof of concept by Greg, whereas on the other hand, there is no proof of concept for the delete snapshot IOCTL, but any interested or well-motivated ransomware group could just Google this CTL on GitHub, and there are many examples of like the Windows source code leak from Server 2003 or XP, and they could re-implement this functionality with minimal effort. As we mentioned earlier, why even bother with trying to evade EDR if you can just run in a world where EDR doesn't exist? So some ransomware families have decided, hey, let's just reboot into safe mode, and within safe mode, we can register our process to run, and we can encrypt it without the worry of ransomware, without the worry of any endpoint security products blocking the ransomware or inhibiting the the actual malicious functionality. So one way to do this would be to use BCEdit. That's what you see all the groups currently using. Um, at the heart, BCEdit, as I mentioned earlier, you can detect this at the command line level. A more thorough detection would be to monitor the registry keys that BCD is backed by, and by monitoring this, you detect kind of all tampering with the BCD, and you can prevent safe boot from being manipulated from both the command line and direct registry entries. So some EDRs do have BCD tampering enabled. So one that comes to mind is Sentinel-1, and they obviously would implement this at the kernel level with a registry callback that's notified on all registry events. So after the ransomware has almost inhibited system recovery from deleting all the backups and shadow copies, alternatively through rebooting into safe mode, the next thing they'd like to do is stop services and different processes. This serves two purposes. The first one is to free up system resources, and the second one is to release handles to files. So, in the example of Conti, we saw down the line that they use Windows Restart Manager to obtain an exclusive handle to the file if the file is owned by a process with an exclusive lock. So by terminating all the processes at this stage, they don't have to do that step later. Additionally, yeah, when you free up system resources, you have more um, resources from the kernel. Well, you've got more room and resources to do the actual encryption process and do it faster. So what this typically is, so with Conti, they have a bunch of whitelisted processes that they won't terminate, whereas in the case of Babuk, they have a explicit list of processes that they will stop. And in the example of Conti, they'll do a snapshot of all the processes. They'll compare it against this list, and whether it's a critical process, obviously they wouldn't want to terminate any critical processes, and then they'd stop them. In the example of Babuk, they just take the snapshot of all the processes, compare them to this list, and if any of them match, they terminate it. So, yeah, as we can see with Conti, it skips all the, they'll open a handle to the process, they check whether it's a critical process, and if it's not, they'll terminate it, and then they do this while iterating through all the files. And the next step is the file system enumeration. So they'll the, they typically, all ransomware has to do this, and the way they kind of do this is that they'll first identify all the drives on the system, and then they'll do a depth first search. So they start in the C drive, and then they look at all the folders and all the folders within that folder, and they see if there are any files that match a certain criteria, and they'll add all these files to a queue, and from within this queue they'll have worker threads that go ahead and encrypt them. Of course, they only queue files that match a certain criteria, so they don't typically encrypt executables, DLLs, or system drivers, and they'll additionally typically skip the extension of their ransomware family. So if it's like .babak, they'd skip .babak files, as they wouldn't want to re-encrypt the file twice. So looking at what Babak does, so they'll starting at the bottom, they enumerate all drives from A to Z, and if that drive exists, they'll go ahead and process the drive, and within this they get the type of the drive, and if it's not a remote drive, then they'll find the paths, the recursive directories from, for example, C drive or the D drive, and they'll always start at the root directory. And we can see here that they use find first file. So given like C, they'll make the search path with C, and then the asterisk at the end. And then if it's not a file directory, no, if the attribute isn't a directory, then it will check if the extension is either executable, DLL, or Babak. And if it is, it'll skip. Else, it will go ahead and encrypt. And we can see that it does this starting at the C drive or the A, B drive or D drive, as we can see. On the other hand, Conti, they check, pretty much the same thing. We can see the only difference is here that they check if it's got the repass point, and the reason they check if it's got the repass point is to prevent cyclic enumeration. So you can create almost like a junction to another directory and have that a directory within that directory that points back to the first one, so you can almost create like a cyclic graph of the file system. And here they just have a function called check directory, which makes sure it doesn't enumerate directories it's not interested in. So example, you wouldn't want to enumerate system32 or the Windows directory, as that's mostly comprised of just executables and DLLs. And if it matches the criteria, it'll insert the directory into the queue list for further enumeration. Else, if it's a file, then it'll check whether the file name extensions are valid, and from here, if they are, then it'll create a task, and it will send the task to the worker threads which are responsible for encryption. As we can see in both examples, they both use find first file, which is pretty much what all ransomware groups does. And we'll see in the next slide that there's an opportunity now for us to kind of hijack this. So find first file on NTFS, it doesn't guarantee to return these files in alphabetical order, so A to Z, but it's almost always that it will return it in A to Z order. So there's an opportunity for security products to almost hijack this, and they can do this by creating their own directories with prefixes on those directories that ensure that they appear first during the enumeration. So what you'll see some products do is either use the $sign in their directory name, so that the directory shows up first during find first file, or they'll have AA and ZZ. The reason for AA is, of course, if it's a queue, then AA shows up first. But if the ransomware group is using a stack, then the ZZ shows up there. And the result is now the ransomware encrypts our canaries first, and we can create almost the detection. So if any ransomware groups, if any application tampers or modifies this file, we can say, hey, this shouldn't happen. Nothing should ever be manipulating these files. It's likely ransomware, and it's pretty good metric of, hey, it's ransomware, guys. So let's kind of look into what these Canary file implementations look like in different vendors. So Elastic, they're great. They've got all of their, well, a lot of their rules open source, and for ransomware especially, we can see they've got massive Lua detection engine, and within that Lua detection engine, we can see how their honey Canary and honey files are built. So they get the telemetry for the file system operations from their kernel driver, and this is a file system mini filter, and this kernel driver sends these rules to the engine, and within the engine they can check, they can do these kind of correlations. So how they actually do the Canary files is that they'll place these directories in known starting points for like ransomware operations. As we saw earlier in Babuk, it starts in the C drive and A drive, but different families, for example, may start in the home directory for a user or the downloads. So they just place it in common locations where ransomware may start to have good coverage. And then they'll create files with random content and random sizes, and they'll use different file extensions, so ransomware is likely to encrypt it. Looking a bit more into the implementation, we can see that they get the Win directory down here. They create all the content. We'll dive into that in the next slide. But then they create their two directories, as we can see, prefixed with AA and ZZ, and they create these directories in their locations. Here we can see, yep, the first thing they do is get all the user profiles, and then they get the directories from this, and then they insert the built content into each directory, and then additionally they'll place it at the root directory, so in the C drive, in the D drive, that all exist. So a different approach to using a file system filter is to use the projected file system. The issue with file system filters is that you need a kernel driver, and it's very easy to write an incorrect or buggy kernel driver that could cause a blue screen. So Windows has almost this provider to allow us to create a virtual file system from within user mode. And the amazing thing about it is that it provides real-time callbacks on all file system activity. So file management, directory enumeration, when a process opens and closes a handle to a file. And what's really important for our case is that we have full access to the buffer when they're writing the file out to disk. So yeah, with the projected file system, we can almost create our own Canary implementation without a kernel driver and have all these operations visible in user mode. And we can also, what I didn't mention is that when these callbacks occur, we know which process is responsible for each of the various activities. And kind of to build these Canary files, I created like an abstraction. We're using an in-memory graph file system where we can just create folders. We can create various random files and set random file times on these folders and files. And to actually create these sample files, I have a variety of extensions, and within the content registry, we can pick one of these extensions, and for each of these extensions, we'll just generate some random file content. We set the content to match the file extension. This is a really important step. So for example, with PDFs, we'll have the PDF magic bytes, and we'll ensure that the magic bytes of the PDF match their content. There's a reason for this that we'll get into later, but the short rundown is that if we have a PDF and we have the PDF magic bytes when we write it out to disk, if ransomware encrypts it and the magic bytes do not match, then we can create almost a detection. Hey, the magic bytes don't match. This is quite suspicious. And this is something that a lot of products do, and it's quite a good high fidelity, low false positive metric of malicious activity. And to actually receive the callbacks, we just specify, hey, we want these various notifications, and we'll handle them. and within the actual handling of that, we can have our detection engine there. And I just have a nice abstraction to specify we want to start our virtualization directory in this honeypot folder, conveniently named, and with all these options. One limitation and caveat of projected file system is that you cannot virtualize directories with content already existing within them. So you can't virtualize the C drive. You can only virtualize directories with no content in them. So in this example, it creates a new directory named honeypot in the C drive, and it create all the content respectively within it. So now we kind of have an idea of what happens before the encryption and the various detection opportunities. Let's dive into what happens during the encryption. So during the encryption, ransomware just takes the files off the queue after the file system enumeration, and depending on the file size and file extension, they'll go ahead and encrypt the file. And they either have two options for this: encrypt the file back out to the same files, so read, encrypt, write back out, and then after it's finished processing a file, it'll rename it. The other option is read the file, encrypt the buffer in memory, and then write it out to a new file, where the new file is the original file with the ransomware extension to it. And then once it's finished encrypting it, delete the original file. And as we'll see later on, this kind of sort of thing makes writing detections harder, as there are a lot of edge cases and a lot of variety to how ransomware can actually do this sort of thing. So to actually create kind of a detection engine around this file system encryption, we can break it down into four sort of categories. We can first index on the process with the process PID, and within the process PID, we'll have like a running sliding window where each kind of activity will place like a score on it, and if a certain process has a score greater than a threshold, we'll mark it as malicious or ransomware. And then when it comes to the actual file content analysis of the actual activity of the file. So for example, we can have different detections here. So is the header valid after a file closed the handle? No, after a process closed the handle to the file and the file was modified. So here we checked whether the PDF bytes, PDF magic bytes are still there, and then we can also do an entropy measurement, taking the entropy of the original file and the file after its modification, and kind of looking at what the delta is and whether the delta is greater than a certain threshold. We can also track the file general management patterns, so whether it renames a file quite a lot. So that's quite an easy detection to have. So if a certain process is renaming like 100 files and this new extension is like .babok, then we can say, hey, quite confidently that this is likely to be ransomware. And the two options here, you can monitor for like known ransomware extensions, or the other option is to monitor for like just generic ransomware extensions. And when it comes to actually applying this detection engine, it's important to ensure that it's optimized, because as we'll see later on, there are a lot of different rules, and applying this to the entire operating system can become quite costly in terms of performance. And what you'll see some products do is apply the coverage primarily to the Canary files, and the main thing here is to ensure the Canary files are placed strategically such that you don't miss you don't miss ransomware operations due to insufficient Canary placement. So let's diving into like the actual detection implementations. Almost all vendors leverage these file system mini filters for their telemetry, and Elastic's almost open source approach demonstrates these various patterns, and they use a scoring based threshold model where if a certain process goes above this threshold, it's kind of almost, they can say confidently that hey, it's ransomware. And Elastic's approach, as we will see later on, has many different detection vectors, including but not limited to the file operations, the the ransomware drops like a ransom note, and known extension blacklists. As I mentioned earlier, during the file system enumeration, when ransomware enters a new directory, what they'll typically do is they'll place a new ransom note. That's these ransom notes have the same kind of language, have a almost predictable file name and file content. So with some regex rules, you can almost detect whether a process is dropping a ransom note. And my implementation with projected file system is I've got these three detection thresholds. So for renaming, whether the entropy delta passes a certain level, and whether the magic header matches the expected bytes. And once I chain these detectors to the detection engine, I can have some responses if this criteria or threshold is broken. And in this case, it'd be to just log the suspicious process and additionally terminate the process. So the first detection is whether the header matches. So when a file is closed and the file is modified, we can check if the name extensions, for example, .pdf, the expected magic bytes are still there, and we can either do this by storing the original file in memory and then just checking it that way. Alternatively, we can just have like a lookup table for extensions to magic bytes and check it that way. So there are a lot of limitations, as we can see, with this actual check. Well, the first way to completely get around this is just not encrypt the first 5-10 bytes of the file. Alternatively, you can just skip the first page. And if a ransomware was doing partial encryption, where they skip the first page and encrypt every other page of the file, this would get around it. Some file types that are text-based would lack these consistent magic bytes, so for example .txt, and they are unable to be validated. And yeah, the headers can still be valid, but the content can, the actual file can be encrypted. And to actually do the validation of an entire file structure and beyond the magic bytes would be quite hard because there's so many different file types, and it'd be quite performance heavy. Of course, yeah, there's the impact of reading the file headers for every write operation, and there's a lot of optimization required to ensure that this doesn't hog up system resources. So in my implementation, we check when we get our detection event, we check whether the file was overwritten or the file was modified, and then we get the magic bytes of the original file and we get the magic bytes of the new data, and we check whether they match. The reason why I'm not getting the magic bytes by the file extension is that ransomware could rename the file first and then encrypt it. In this case, if I was detecting the magic bytes by like .pdf, then I wouldn't be able to get it. As you can see, there are a lot of edge cases, and it's quite hard to do this correctly. Another option is to detect it with entropy jumps. So when ransomware encrypts the file, encrypted content, the entropy is typically higher than previously. And that's a good indicator. You can either have like a linear scale where if it hits past a certain threshold, well then it's malicious, or you can do a scale where it's if the entropy jumps by like 10%, then it's maybe not so malicious. Whereas if it's like 60%, based on like an exponential scoring system, that's very, very malicious, and that should never really happen. There are a lot of limitations though. If you have partially encrypted files, well then that may not hit that threshold, and that's where it comes back to doing it with a linear scales kind of thing. And if you've got pre-compressed or encrypted files that are correctly encrypted, by the very nature of being compressed or encrypted, their entropy is already quite high. And if you want to completely just get around this, well then you can just pad the encrypted content with null bytes and lower the entropy of the entire file. And of course, as with all these detections, as you see, there are a lot of tuning challenges to ensure you don't have false positives in a system. And as we can see here, we just compute the entropy of the original data and the new data. And if that's greater than the delta, we can say, hey, this is malicious, and we can give it a score. A better solution would be to have like an exponential scale where the delta increase as a percentage. Where if the increase is low, then it doesn't really deserve a score. But if it's high, then the scoring should be much higher in respect, and it should almost be an exponentially higher score. Another detection metric is file renaming in a short period of time. As I mentioned earlier, we would typically have all these detections in with a TTL, so we're not looking at a process for its entire lifespan. We're only looking at a certain process indexed on a PID in a sliding window. It may be the 300 seconds may be greater than the entire process lifespan, but it may be shorter. So yeah, we just want to look whether a file renames a group of files to another extension in a short period of time. Of course, there are a lot of limitations here. Like if you've got certain batch operations, then these batch renames that are legitimate can be almost malicious. And you can kind of just get around this by just creating the encrypted file as a new file and then deleting the original file, as I mentioned earlier. And one step past this, ransomware doesn't even need to encrypt the file. It can just encrypt and write out to the same file with no renames. I'm honestly quite surprised no ransomware groups do this, because to actually decrypt the files, they just need to check whether the metadata that they append to the end of the file exists. And of course, to get around a lot of these detections where the detections are indexed on the process ID, you can distribute the file encryption, the renaming across a plethora of processes. And what we do here is quite simple. As we can see, if on file rename operations, we just track it against a certain process, and if it exceeds the certain count, then we can give it a score, and it's quite simple. To get around the second scenario here, where the ransomware creates a new encrypted file, then deletes the original, something that Elastic does is that it tracks the history of a path. So if this gives a more holistic overview to the file system's activity, and it helps detect the scenarios where a file is deleted and the encrypted variant is written out before or after. But again, there are a lot of high false positives on batch operations, and it's quite hard to match all the various edge cases that may occur, and it's very much cat and mouse game, as you guys can probably guess. So looking at their detection, they check whether so in the ransomware encrypts the file, it writes it out to a new file with the extension name, and here in this scenario that would be stored in path event table. And then if the entropy of that file was high, and then this file was now being, the original file was being deleted, we then create a new score that delete with high entropy where it was previously created. It's quite complex, and as you can see, if you look at the detection engine, it's a couple thousand lines. There are a lot of edge cases to consider, and it's it's quite hard to have something that's comprehensive. And to say that, to prove that like my projected file system implementation wasn't all fluff, I ran it against Babuk, and hey, as we can see, it detected and terminated it based on a suspicious file rename count. But with all good things, there are a lot of caveats with the projected file system. The API is quite complex, and MSDN in true Microsoft fashion lack documentation, and there are only a few examples. By default, this provider isn't enabled, and you have to enable it manually. and to actually run or virtualize a directory, you need administrator privileges. And ransomware can detect a directory as being a ProtoFS virtualization route. If you guys remember a lot earlier, Conti had this file attribute repass point check. That would in turn detect ProtoFS because ProtoFS has this attribute on these directories. Oh, where are we here? And yeah, as we can see here, you can detect it by checking the repass point if that attribute's there, and they can then, as a result, avoid ProtoFS directories. And the biggest caveat, I think, is you cannot virtualize existing directories due to the nature of ProtoFS. So you're not unable to see the telemetry of that directory. You'd have to create a new directory and create your new content within it, and then virtualize. And that kind of forces you to have a file system driver. And yeah, while it's cool to see that it can be done. I don't think, yeah, it's the best approach. And the big gaping hole in kind of all of this is that what if ransomware ran before EDRs had an opportunity to start? So we saw in the earlier on that there was an opportunity to use SafeBoot, and within SafeBoot, no endpoint security products would be running. But what if you ran, with boot execute before the Windows 32 system initialization? Here, from within this, I'm quite surprised no ransomware groups have done this yet, but with boot execute, you can register an unsigned application to run before Windows 32 system initialization. So all these EDRs, the services, the drivers, the other ransomware detection and prevention products, the backup products, they all run after or during Windows 32 system initialization. And from within boot execute, you can disable these services. You can manipulate volume shadow copies, as if we remember on like page 5 here, these shadow copies exist within the device global namespace. So within boot execute, you can have ransomware that manipulates and deletes these shadow copies. And EDRs would have no visibility, even if they had a mini filter that ran and intercepted these IP requests in the kernel. They would have no visibility into the manipulation and functionality that a boot execute process has. Currently, vendors may detect boot execute as persistence registry key, but they don't do several things. They don't remove this persistence. They don't verify the signing requirement of these applications, and they don't have any sort of anti-tampering. And something you'll see is that a lot of these vendors miss these new registry keys that get added in Windows 11 and newer versions. The main reason for that is a lot of their detections were created in reference to the auto runs utility by Mark Rusinovich, and Mark Rusinovich's utility also doesn't capture these new keys because, well, it's not maintained. So I think it's really a massive gap that endpoint security products don't do any sort of validation of boot execute registry keys or prevention, because if you can run before the system initializes, you have the ability to manipulate shadow copies, tamper with EDR drivers, tamper with everything, and they have no visibility. So, for example, to look at what it looked like with tampering with CrowdStrike's services, we can modify the CS Falcon and CS Agent service entries, and we can change the start key and the type key to disabled and Win32 own process. This works to disable both their services and their kernel drivers, and it prevents them from being loaded. The other option, as some of you guys may remember, is to just delete the CS Falcon service executable from disk. We don't have the same level of, we can't do the same with the agent, as the agent is in the system 32 and there's um, a level of access control that prevents us from doing this easily within boot execute. So the easier option is just to modify the registry keys so it doesn't boot. Hey ho. What these vendors kind of should be doing is validating the entries in boot execute so this tampering isn't allowed. Like, I really just want to double down on the fact that these applications are probably more like in terms of privileges on Windows and like capabilities. Boot execute is incredibly powerful. For an executable that's unsigned and with only administrator privileges to be able to tamper with services and kind of the entire system, it's insane. Like, this shouldn't be allowed. They should really be doing some sort of validation checks with elam to ensure that all the entries have valid signatures before they're able to execute. And once they've validate or invalidate these entries, they should remove them and prevent them from being executed, thus preventing ransomware and tampering during this stage. It's worth noting that during boot execute, the system won't continue until the boot execute entry is fully like the process is fully complete and returns. So it's synchronous in the sense that it waits for this to be finished. So kind of the key takeaways I want you guys to have from this talk is that detection is really hard. It's a cat and mouse game. The approach with using Canary files is a losing battle. Like, there's so many limitations to it, and it's so complex to do, and so many edge cases to get it right. What vendors should be focusing on is ensuring the integrity of the VSS service, and this is because when Microsoft created it, it wasn't created with security in mind. It was created more as a backup solution. So ensuring that these backups aren't able to be manipulated by even administrator applications ensures that the destructive operations such as resizing or deleting are prevented, or some sort of access control. They should, instead of focusing on having naive and shallow detections on the command lines, they should focus on filtering IRPs to ensure that, hey, no one malicious or no one that shouldn't be doing it is allowed to call these IRPs. And with that, do we have any questions? Oh, any so For Alpha Fox asks, for companies who use CrowdStrike, would you recommend having separate detections for these command line executions? And if so, how can we be sure that the sensor will catch those for the alert to fire if the threat actor has a way to bypass the EDR? So I think there is value in having the command line detections. I don't think you should be creating additional detections. I think you should push CrowdStrike to focus on the adding some sort of IRP filtering at the kernel level and having that sort of filtering, because while you can have, like, yeah, the command line and then you can evade the command line by running it in memory, or you can have that IOCTL. If you don't have detections for the underlying IOCTL, then there's no value in having these almost naive detections which give you a false sense of security. Um, Elastic's detection engine, so yeah, it all runs agent side, and within the agent they have their Lua detection engine here, and then this detection engine runs on the endpoint, and this just consumes telemetry from the various telemetry providers. So boot execute is only for services and drivers. No, boot execute is for any unsigned application that is a native application. So the only caveat to boot execute is that it needs NT process startup. That's what it needs its entry point to be um, as opposed to, so yeah, to create a native application, you need to specify the entry point, and you can only use Windows native API functions. Considering partial encryption seems much harder to catch detect, how commonly used is it? Um, it's harder to detect because the entropy of the file before and after with partial encryption, it may not jump too much. A lot of ransomware uses partial encryption. I think when it comes to picking which type of encrypt, well, how much you want to encrypt a file, it depends on the file type. So if the type of the file cannot be recovered easily, then the ransomware, well, it may encrypt a bit of it, and if it really depends how the file is stored on disk and how recovery works for that file. Ransomware may still prefer full encryption just because it completely stops any sort of recovery at the file, like restructuring or from the metadata. Um, it seems, yeah, a lot harder to catch and detect, and it is. Um, the full encryption just has like the kind of guarantee that there's no element of recovery, um, if like, yeah, if there's like a forensic guy that tries to rebuild the file from scratch or elements of the file, doing like the full encryption eliminates that step. Yeah, I mean, yeah, there's that too. But like, for example, if you've got an encrypted database on disk, and the extension is like something if you like ransomware, then you only have to encrypt like less than 10% of the file for it to become completely obsolete to recover, because you completely prevent recoverability. But if it's like a PDF, if you encrypt like 10% of it, then a lot of the content is still enabled. It's still there because it's like a text-based document. It's not compressed, and it's still recoverable. Are there any other questions? So, do you see a move by ransomware developers who are on the RAS business model where they're reducing their evasion capabilities and becoming an encryption tool for affiliates? As if ransomware developers in the but expect affiliates to do the hard work and only provide the file encryption software and their infrastructure to ask the ransomware. Um, I mean, obviously with ransomware, there's always like the ransomware software as a service providers who enable the capabilities, such as like Lockbit. And I mean, the thing with ransomware is that it's not terribly hard to write. I don't do much threat intelligence, so I'm probably not the best person to ask this sort of question. Um, I think where I see like ransomware probably moving is less with the pure encryption model and probably towards the exfiltration. Exfiltration is its complete own problem. It's a lot harder to detect. Like DLP is a much harder solution. Um, so that's kind of where I see ransomware groups probably going towards. Is just like pure exfiltration, because with exfiltration, um, it doesn't matter if a company can recover files. If they've exfiltrated them, only the ransomware provider or operator can guarantee their deletion. The values in the data, not the business recovery. Um, I'm not sure that quite answers your question. I'm not probably the best person to answer this ask this question. Any other questions? Yeah, with to run safe mode, you have to register um, your application to run as in safe mode, and then you obviously have like some sort of persistence mechanism, such as the run once registry key, and then when you reboot into safe mode, the run once registry persistence starts your application, and then you run as you're registered in the safe boot. On that note, I think, yeah, thank you guys for attending. Obviously, I will make the slides available shortly. And yeah, if you're interested in the Project F stuff, that is available on GitHub, ransomware here. But yeah, I don't think this approach is good. I don't think Canaries is what people should be doing. I think you guys, vendors should focus on um, ensuring the integrity of VFS. And yeah, probably like the best approach would be to no VSS. Best approach would be to have these backups at a remote location where they have very high integrity and no one can maliciously push backups to that location or delete them. Storage is cheap, and people should leverage the fact that storage is cheap to make as many backups as you can that aren't on the same system, and the integrity of the system doesn't compromise the integrity of the backup. All right, yeah, thank you guys for attending. I hope you guys learned something, and have a wonderful day.